voltage that stops stuff. Okay, people, in this one we're going to talk about the wave-particle duality. So a duality is two things at once. The wave-particle duality in terms of light is where we're likening light to something that behaves like a particle, travels like a wave. So two branches of physics years and years ago. So there was the Thomas Young bunch of mates. Light did the interference pattern, Young's double slit apparatus, blah blah blah, proved that light is a wave. But then we had someone like Einstein with the photoelectric effect, and it's kind of what this apparatus is here. And he was looking at light behaving like a particle. So light is a particle. We call a single particle a light photon, and these photons kind of behave like waves. So they interfere, they reflect, they refract, they diffract, all of those sorts of things, so that they behave like a waves. And the energy of each of these individual particles of light is given by E equals hf. H is Planck's constant. So Max Planck, one of Einstein's mates, I think, might have actually been one of his advisors. Planck's constant to do with the energy of individual photons, and it comes up in the photoelectric effect, and I'll draw a graph and hopefully it'll explain it with this sort of stuff over here. So we can use Planck's constant to find out, the frequency of a wave multiplied by Planck's constant will give us the energy of the wave, energy of the photon. Sorry. So the higher the frequency, the higher the energy. So you look at infrared. Has a pretty low frequency. Infrared makes you feel kind of warm on a summer's day, or is the heat coming off the radiator bar heater fireplace sort of thing. Then you go into the reds, orange, yellows, green, blues, indigos, violets, and then you get to ultraviolet. So this one here, infrared, is the one that makes you feel nice and warm. Ultraviolet is the one that causes skin cancer, sunburns, and things like that. All right. So this one here obviously has more and more and more energy involved. What I'll do is kind of shift that so it's not in our way for the next bit. Okay, now Einstein, when he was looking at this photoelectric effect, he was looking at the interaction of photons and electrons in the surface of things. So this here, we're going to have a target, a piece of metal that's going to be our target, and we're going to use something like sodium or potassium because they're fairly reactive. Their electrons are obviously, because they're a little bit more reactive, their electrons are slightly looser in how they're bound to the nucleus. And what we're going to do is we're going to shine some light on it. So we're going to shine some red onto it. Now, red has, again, it's pink, red has a certain amount of energy per photon based on E equals hf. And for sodium, this red light, I don't think is quite enough to make anything really happen. So as we get into the surface of this metal, we have, a whole bunch of electrons that are, below the surface, and they're whizzing around all over the place. And this photon of red, again, it's not red, comes in and hits one of these electrons. Now, because this photon is a packet of energy, it can directly hit one of these electrons, give all of its energy to that electron. What that's going to do is make the electron jump, move into an excited state, or orbit, move around in there a little bit faster. And if it's going fast enough, this electron can actually escape the surface of the metal. So with red light, I'm pretty sure it's not quite enough. But with green light has a higher frequency, therefore it's got more energy, therefore it's going to give more energy to these electrons, to the point where they'll start jumping off the surface. And if we have a whole bunch of these electrons jumping off the surface, we can sort of capture them, and that's sort of what this device is here. So we have a bunch of filters, and we're going to pass white light through it. White light is all of the colours. The filters are going to let us split up the white light and just let red or yellow or green or blue or whatever it is through there, and we're going to make it hit sodium. And now sodium is unique with the amount of energy it takes, the amount of work you need to do to these electrons to get them to escape from the surface. And once they do, we can actually detect them with an ammeter, an incredibly sensitive one though. So if we shine a bunch of light onto the surface of sodium, we'll get a stream of electrons come off. Now, this stream of electrons is going to have a bunch of energy. It's going to have a range of energies. So you'll see that some of these electrons are kind of near the surface. They're easier to strip away. They don't need much coercion, I guess, to jump out of the surface. For the ones that are further down and further down and further down and further down, they're going to take more and more and more energy to get out of the surface. So we're going to have a whole bunch of electrons moving at different speeds. And because we have all these electrons moving at different speeds, it means that we have to do less work on them to get them to stop. So if we had an electric field, so positive plate, negative plate, and we made these electrons move towards the negative plate, if we made them move faster, they're going to get further through that field. If we make them move slower, they're going to get less far through that field. And that's kind of what we've got setting up here. So we've got a potential difference that we can control. So that we can control, so that's variable. We've got a potential difference that we can control. We've got a negative plate here and a positive plate here. So what that means is that our electric field is set up so that we're trying to accelerate the electrons back towards the surface of the metal, I guess. So the energy that comes in from the photons has to be a fair bit in order to get these electrons all the way over here. Now, what we're going to do is we're going to shine in a bunch of different colours. So we're going to have reds, blues and greens, and the reds, I'm going to say, aren't enough to get electrons to jump from the surface. There's quite a big possibility that it's actually okay. I'm pretty sure greens does work. So green will let electrons jump out of the surface, and it's going to get them to have a range of energy as they come out. Now, let's say that we only have these sorts of electrons coming out. All right, so I can set up a potential difference which is going to make an electric field from this side here to this side here. So it's going to have an electric field going that way. Remember, electrons go opposite to the direction of the electric field. So it's going to push them back this way. Now, if I have it set on 0, so no field, all of these electrons will make it through. Anything that comes out of the metal surface will get over here to the negative plate. And then they'll be detected by the ammeter, and you can see that there's a current flowing. And as I wind this up, little bit by little bit by little bit, the ones that have got the least amount of energy, they're going to stop because it takes less work by the electric field to stop them. W equals Q delta V, remember? So these are going to take less and less and less energy to stop. Now, after a while, we're going to get to a point where we've stopped all of them. So we're detecting 0 current, and whatever that says on our voltmeter, our potential difference, that is what we're going to refer to as our stopping voltage. All right, because it's the voltage that stops stuff. Now, as we shine blue light in, we're going to get photons with a slightly different range of energies. And in this case here, what we're going to get is, electrons moving faster in general. So they're going to have, takes the same amount of energy to get out of the surface, but these ones are going to have more energy left over once they've left the surface. And because of that, it's going to take more of an electric field from the potential difference to stop them from getting across there. So from this, we can actually find out the minimum work it takes to get an electron to escape. So we can look at Planck's constant times the stopping frequency is an energy. Energy, remember, is work. Work is Q delta V. So we can work out the stopping voltage related to what's considered the threshold frequency. So F0 is the frequency below which no electrons will escape, no matter how bright the light is. All right. So if I have a bajillion photons of red light, and red isn't enough frequency to get any electrons to come out, nothing happens. If I get a really, really, really dim blue or purple light, we'll actually get electrons coming out. And they'll have a fair bit of energy. If I get something green, we'll have a fair, some coming out with some energy. All right, so the amount of energy in our system, or the amount of energy into our system, E equals HF. The amount of energy that's used up by electrons, coming up to the surface, is W is HF naught. The energy left over is the energy that these things will actually have to be able to move through the electric field. So we've got some sort of K max, kinetic energy max, left over. So Einstein had this idea, using conservation of energy idea, that if you put a certain amount of energy into the system and use a certain amount up, there must be a certain amount left over. So this is our work, our Q delta V that it takes to get across this field. So K max is HF minus W. So all I'm going to do is rearrange it. So this guy here, whatever's left over is equal to what you started with, take away what you've used up, where W is the work function and H is Planck's constant and F is the frequency of the light that we're using. And what Einstein did was he came up with this idea, and then of course, because he's a brilliant man, he did an experiment. And what he found was that if he used, if he used various frequencies of light, so frequency increases, what it took was more stopping voltage to get these electrons to stop, and more stopping voltage to get them to stop means that they're going faster. So we can relate the stopping voltage to the maximum kinetic energy of these electrons as they're leaving the surface. So he's got himself a bunch of data points, and he's drawn himself a bit of a graph, and then he's decided, I know, I'm going to plot a line of best fit through there. The slope of this line is HF. The point that it crosses the x-axis here is the threshold frequency, and it just so happens that the starting energy of all the electrons is the work function, which is down here. So if we have zero frequency light shining on it, the electrons have this much energy that they need to at least reach the surface before they reach the threshold frequency, and it's only once you get above that you can actually get these things escaping from the surface. Alright, so Einstein came up with this idea in 1906 or 1905 or somewhere way back when, and it was considered his miracle year. He probably should have won a Nobel Prize for this, but he didn't. Probably should have won Nobel Prizes for 3 or 4 of the other things that he did, but he didn't. But yeah, here is experimental proof using the photoelectric effect. One photon in, one electron out. Just as an aside, you can't have a red and a green add up to equal a blue and get extra energy out. One photon will be absorbed by possibly one electron, and that electron may or may not have enough energy to escape. If we wind the brightness of the light up, we'll get more electrons out, but they won't have any more energy. If we wind the frequency up, we won't get any more out necessarily, but they'll have more energy when they come out at the end. All right, so Young's double slit, proof that light is a wave or behaves like a wave. Einstein's photoelectric effect, proof that light is in fact a particle. We use this these days on those little sensors where it goes, there's a buzzer when you go into a shop. We use them on smoke detectors. We use them with photovoltaic cells, so solar cells, things like that. Fantastic idea, and it's still paying dividends for us today.